Welcome everyone to the Edge AI Lab with Microcontrollers Session. This particular session is conducted by MLT Edge AI Lab. And let me just briefly talk a little bit about MLT Edge AI Lab. So this lab started all the way back in 2019 when a small startup in Chiba called as Hacker Farm. They invited some of the researchers from machine learning Tokyo community, and they had a real problem. The Hacker Farm, these guys had a greenhouse in Chiba, and they were experimenting with a suspended robot on this particular greenhouse. So they wanted to see how machine learning can help to solve the real life problems. So a bunch of engineers and researchers went there to Chiba, and then we talked with the farmers, we talked with the local people, try to see what are the problems they are facing. We also tried to work on the suspended robot, which was installed in the greenhouse. So that was, I think, the main spark which created we really need to understand how we can combine machine learning with hardware. And with that, I think we started the first hardware working session, which was a collaboration between MLT and Robot Club. Wherein like on a weekend, we organized a hackathon, ideathon hackathon kind of session for around like 4 to 5 hours, where we had all the devices like Raspberry Pi, Jetson Nano, Google Coral, Arduino. And we had an open environment where people could experiment with these devices, and they can try to brainstorm ideas and then implement them, make simple, quick prototypes with them. So that gave us the direction of MLT EdgeAI Lab, which gives us our main aim is to create an open environment where everyone can easily access these materials and try to build their own apps, EdgeAI apps, using the hardware available. So then in 2020, we also participated in one of the AI Edge contests hosted by Cynate, where like a team of 5 engineers, Alisha, Katosan, Naveen, me, and Ben, we tried to participate in the this particular contest, which was based on developing an algorithm and a model which can do object detection and tracking on an autonomous vehicle. So we did like a model submission, and eventually we had we were glad we ranked third place in the competition. So but just after the competition, we also deployed this particular model on a real device. Here we took Jetson Nano, 3D printed the case, and then deployed our model on this Jetson Nano and installed this device on the bicycle, so that we can try to see how actually it is effective on real case data. So if you want to do this kind of exciting projects, please join Edge AI Lab on MLT Slack. The MLT Slack link has been posted in Zoom chat, so please take a look at it. So with that, let me just introduce this series. This series is the reason why we wanted to have such kind of series is after our last session last year, it was a COVID situation where a lot of things happened and we couldn't have the opportunity of making these sessions available offline. So we were thinking for a long time how we can build this online sessions and do a collaborative activity or a workshop session. So with that, I think we thought it's maybe a better way is to organize short series, like a weekly series, so that we can try to experiment with some small prototypes in a very short time, and then work together with other members. So the basic aim of this particular microcontroller series is to help you build your Edge AI application by the end of this series. And we divided this entire series into 4 sessions. And right now we are on the 3rd session, which is audio-based application using microphone. Naveen will give us an overview and walkthrough of how to build an audio-based application using a microcontroller. So with that, let me just give the handover to Naveen to quickly introduce Naveen. Naveen, can you please introduce yourself?
Thank you, Yuraj. Hi, everyone. So I am Naveen Kumar. So I work at RIKEN, one of the largest research organization here in Japan, as a senior technical scientist. And I mostly work with microbial genomic data sets for the data analysis and some machine learning. And in my free time, I usually like watching movies and doing the nature photography and mostly actually playing with microcontrollers. And you can see all of my projects here at hackster.io. So I have created many projects, mostly related to the Edge AI and with the diverse nature. So please check it out. And you can find all my new updates at my Twitter handle, Naveen. Thanks.
Yeah, thank you, Naveen. Every time I say this same thing, like whenever I see this board, it's like really exciting to see different types of projects with hardware, and like it's really nice. Like we can do a lot of things just at home. We don't need very hi-fi sometimes instruments, like some basic stuff, and you can do a lot of things. It's just like I think ideas, and Naveen's ideas are really nice. I like those. Okay. Let me also introduce myself. So I am Yuraj, and I'm the co-founder of MLT, and I'm also leading the Edge AI Lab. So I'm working in a software, so in an e-commerce company, and right now I'm a engineering manager for a small team of engineers. So the main hobby, I love eating food, and I like playing with robots, especially with the kid robots. So you see, in my past projects, I had this like a small Plen robot in the middle image here. You see, this is a open source software, open source humanoid, which you can easily just search and get download the 3D prints. And I wanted to build my own humanoid, so I started 3D printing this and then try to control it using motors and a basic Arduino app. And then previously, I also worked on Raspberry Pi based robocars, which were like designed for kids, using the basic Tamiya kits and Raspberry Pi and Scratch software. So with that, let me just go to the blocks of AGI pipeline. So till our this in the previous past two sessions, session 1 and session 2. Session 1 was the overview of AGI pipeline, and session 2 was the how to make a motion-based application using accelerometer on a microcontroller. So we overall divided this full pipeline. We think like this is like a generalized pipeline for any particular AGI application, where the basic thing comes from data collection, storage, which partly occurs on the edge, and then your model building, pre-processing, model building, model tuning, post-processing all occurs on cloud or PC. And then once you are ready with the model, then you again go back to edge, where you try to deploy this model on the device and then do inference. So with this generalized pipeline, let me just hand over this again back to Naveen, where Naveen will today take us through overview and also explain how to build an audio-based application using microcontroller. So Naveen, can you please take it away?
Yeah, thank you. So let me share my screen.
Yeah. Yeah, we
so
can see you.
Actually already told about all these pipeline blocks, and we already discussed many times in the previous two sessions. So just for a quick recap, so we will be actually doing most of the data collection and data storage on the edge device. And for data storage, it's kind of hybrid approach. So in this current project, we will be doing data storage on the cloud. And we will run all the pre-processing to the post-processing blocks of the pipeline on the cloud. And then we deploy back the model on device and do the inferencing on device. So let's first talk about a little bit example of the Edge AI application using microphone. So you can see here in the pictures, so there are 4 projects I have already created at hackster.io. So you can find it using this URL given here. And these all projects actually mostly do the audio processing and inferencing using the audio data. So for example, detect audio event. So in one of the first examples, so actually I am doing the running faucet detection. So if you are, so suppose if you forget to the faucet running, then this microcontroller actually start beeping or will send email notification. So this is some kind of alarm notification system. And another one is the Sonoring Guardian. So this is the project actually we will talk in detail later in this session. So in Sonoring Guardian is actually just detecting the respiratory sound. So it could be like cough also, but snoring is also one of the part of that. And other two projects, actually, we are doing keyword recognition. So keyword recognition can be like you can give some kind of command to your robotic system or maybe home automation systems. So these are actually the use cases of the Edge AI application using the microphone. So we will be actually using the Arduino Nano 33 BLE Sense, and which we already used in our previous session for the accelerometer application. So this time we are going to use the microphone, the onboard microphone. So you can see, so the microphone is actually highlighted in the red oval here. And this microphone, which is on board of the Arduino, is omnidirectional digital MEMS microphone. So omnidirectional means it can take or listen from any direction, and it is the based on the electromechanical system microphone. So it is a digital kind of nature. And this is some kind of the particular part number from the ST microelectronics. So we have to use the library for this part. And this microphone actually uses the PDM output, that is the pulse density modulation. So we will learn a little bit more about this in next slide. Sorry. Okay. So the project, actually, we are talking about the snoring sound detection. So snoring is actually caused by rattling and vibration of the tissues near the airway in the back of the throat. So you can see in the picture. So there is an airway actually. So this airway actually has the vibration, and it actually generates those kind of noise or snoring sound. And the aim of this project is to detect the snoring sound during sleep. So we are not actually monitoring all the time, just during the night time when you sleep. And we will understand the data collection process for this microphone audio sampling. And we will be doing the digital signal processing to extract the feature. So we will understand how we can do this kind of process. And for this demonstration or making this project, coding is not much required actually for simple working demo. But if you are an advanced user, so you can take the code, the source code, and you can customize for other use cases. And for the rapid prototyping, we will be using the Edge Impulse Studio. That is a cloud-based toolchain. So first thing is, what is pulse density modulation? So pulse density modulation is similar to the PWM. If you have already using servo motors or driving other kind of motors, so you must know in Arduino like how you can use the PWM interface. So for this audio data collection, actually, so audio data is in physical world is just the sound pressure in air. So we have to convert that thing, the pressure in air that is in analog nature, into the digital nature. So using the PDM, so which represent an analog signal with binary signal. And PDM is somewhat third kind of microphone interface. So we can integrate with microphone, which is apart from analog or I2S. So I2S and analog is the other two kind of interfaces. So you can connect the electric microphone directly using the analog interface, or you can use I2S based microphone. But in this project, we are using the PDM based microphone. And PDM is like 1-bit PWM. And in the image below, you can see this is just an example of a sine wave with the single period, which is sampled at 1,100 times and represented as a PDM bit stream. So it just calculate the density. So you can see where is the density is high. So the waveform amplitude is higher in those parts, and where the density is low, so those are all 0 parts and the amplitude is very low. I mean, not low actually, in the other part of the amplitude, so negative. Yeah. So first, to set up the software and the hardware, so actually it is assumed that we already have the Arduino IDE and Arduino core for Nano 33 BLE Sense are installed on our system. So we already showcased this practice in the previous session. But if you have not done or you are new in this session, so maybe later Yuraj will give a walkthrough of our GitHub repo There we have documented everything, so you can actually do from the scratch. And we are actually using a vibration motor, which is used as an output, and it displays the, so in the previous session, we used LED for the displaying the output of the accelerometer-based application. But in this session, or in this project, we will be using the vibrating motor to detect if there is a snoring sound. And it requires a little bit of basic soldering skills. So you have to just solder 3 wires to the Arduino Nano BLE to connect this vibrating motor. So you can use any kind of motor. So I'm just using one generic kind of motor. And one thing you have to keep in your mind, so if you are using Arduino Nano 33 BLE Sense, so their pin are not output 5 volt. So there is one pad. So this pad actually is disconnected by default in the factory calibration. So you have to actually breeze this. So this is highlighted in the red on the board, and you have to use the solder to breeze that thing. And once you are done, then you can use the 5 pin to provide the power to this vibrating motor. So now we need to do the data collection. So in the previous session, actually, we connected the hardware directly to our laptop or PC, and we just sample the data online. But in this project, we are not doing online data capturing, because the data is actually very difficult to actually sample in real time. So you cannot get all kind of snoring and other data set, other type of data we are using. So for this practice, we are actually using the audio set. So audio set actually is a large scale data set of manually annotated audio event. And we downloaded the snoring and other nature sounds. So to distinguish the snoring from the background noise. So you can see in the list on the right side. So along with snoring, we also captured or extracted the sound of vehicle or toilet flush, rain, etc. From audio sets. So audio set actually just give you an annotation of the data. So it consists of an expanding ontology of 632 audio events. And those are actually human leveled or annotated by human for the 10 seconds of sound clips. And those sound clips comes from YouTube video. So for example, they have just annotated like in YouTube video. So this is the URL, and from the second 10th to second, 20th second, so there is snoring sound, or from maybe 1/20th second to 1/30th second, there is sniffing sound. So you have to actually extract those from the YouTube video. So we will only given the URL of that YouTube clip and the annotations of that and level of the data. So the audio are extracted from the YouTube video of the select events and they're converted into the waveform. So when you extract the audio from the YouTube video, so we actually convert those into the wave audio file format, that is the WAV. And we use the 16-bit depth single channel of data, which is sampled at 16 kilohertz. So actually, we will also provide the script for extracting this thing. So everything is automated. And I am going to show you one of the example. So one of the snoring example, which I have captured. So how it looks like, sorry. So this is the 10 seconds of the data. So, and all other sounds are like similar nature. So you have now feel of how does it look like. And for the data storage, actually, we are using the edge impulse. So where we will be doing all kind of pre-processing and the data signal processing and the training of the model and deployment, creation of the deployment bundle. So for that, you need to register a free account at edgeimpulse.com and create a new project. So that is the easy process. And also you need to install the Edge Impulse CLI. So that is the command line interface on your local computer. So we also given this kind of information in our GitHub repository. So maybe you can later consult with that. So you don't have to remember everything on this page. And we will upload all the WAV file which we extracted from the YouTube videos to the Edge Impulse using the command line shown here. So, and all the data set we will upload to the Edge Impulse will be automatically split into the training and the testing sets using the commands above. So actually in this command, the second command, we are using the level snoring and the category is split. So if you provide the category as a split, so it will automatically maybe 80% of the data in the training part and move the 20% of the data in the testing part of the data set. And once we are done with the data upload, we need to talk a little bit about the feature extraction from the audio clips. So for feature extraction, actually, we are using the spectrogram. So a spectrogram actually is a visual representation of the spectrum of frequency of non-periodic signal. So audios are usually non-periodic. So sorry. So audios are usually a non-periodic signal, and spectrum of frequency is actually you convert the audio waveform in different amplitude and phases. So those are the spectrum of frequency. And spectrogram is really good for audio data, for non-voice recognition. So actually there are other ways to extract the feature from the human voice. Those are actually MFCC or MFE. So using the male frequency. So those are different kind of algorithm. But this is actually, this data is actually non-voice. So this is just the respiratory system sound, like coughing. So snoring is not a voice thing. So that's why we are using a spectrogram, which actually works really good for the data extraction. And for the extracting the data and the feature from the data or the signal actually. So spectrogram extract the time and frequency feature actually, both. So in the previous session, we see like using the feature extraction, we only used the frequency, but this time actually we are using the both time and frequency in the single feature. And so the procedure is we divide the window. So window is your audio sample in multiple overlapping frames. And each frame is actually then divided in frequency bins. So actually your audio sample is a mixture of the frequency. So we divide those frequencies into the different bins using the fast Fourier transform. And then we calculate the power spectrum. And though all these things are actually captured into the spectrogram, and these all things we will be doing on the Edge Impulse Studio. So all things are actually automated, but we have to understand what those things are. So this is the digital signal processing procedure we are doing. So on the top row, you can see this is the audio raw data, which is sampled at 16 kilohertz. And when you sample the data using the PDM microphone, you just give in Arduino, you just get the integer value, like positive integer or negative integers. And we actually, and if you see those things in the waveform, so it looks like the image, first image. And we actually, so this image is actually taken from the snoring sample. And snoring sample is actually kind of periodic. So the waveform itself is, I mean, non-periodic, the audio sample, but snoring is, I mean, it's like not a periodic motion kind of thing. So we actually have to remove the intermediate part, which are actually could be the background noise, like some television is playing or there are some nature sounds. So those parts become the features. So we have to actually remove those parts. So using the Edge Impulse actually, so we split the audio waveform and only extract those part of interest where the sonoring sound is dominant. So for example, this waveform is split into the three segments, and though each of those segments actually pass through the FFT, and we generate a spectrogram for that FFT. And we use the 200 millisecond of window size and 1000 millisecond of window increase. So it's a 2 second and 1 second. So window size is actually like what is the length of your frame of the audio sample? And window increase means like how do you slide? Like how, so for example, if you have a 10 second of the data, so you just capture the 2 seconds of the data, slide the window every time, like 1 second of increase, and generate the spectrogram for each of the frame. And this way, actually, we generate the data, do the data processing of the audio samples. And in this demonstration, actually, so I have captured all the end-to-end pipeline through the video. So in this video, I will show you how I have done that. And whenever possible, I will stop the video also. So actually, after creating the edge impulse registration, so you can go to the data acquisition page. So I already have collected many data samples for different nature sound with the sonoring. And then we have to actually go to the, so you can see here we have the training data and the testing data sets. And for uploading the data set, actually, we will be using the Edge Impulse uploader, which is the part of Edge Impulse CLI. And then we will just use this command line, and all the wave files which is extracted from the YouTube video will be uploaded to the Edge Impulse Studio. And this is one of the sample I have uploaded here. And you can just split the samples into the segments using this, the menu, drop-down menu. And it will open this window, and then you can just, it will automatically recognize all the segments of interest, and everything is okay. Then you can just click on the, do the segmentation. It will create the three segmented files or wave format. Then we actually create a impulse. So for that, actually, you have to create a, we have to create a DSP things. So I have selected the spectrogram for that, and then chosen the KRAS for the classification. So we will be using the neural network for that. So let me enlarge the video. Yeah, so you can see easily now. And then you have to go to the spectrogram where we will configure the spectrogram. So you can actually choose all the frame length, frame stride, and frequency. These are all the parameters. Actually, I have set that for the FFT. And you can play with these things, which is, so this is kind of experiment you have to do. And once you save the parameter, then you can actually generate the feature. So I do the fast forward this thing, so it will take a little time. So once the feature extraction is done, so it will create a visualization. So you can see on the picture, sorry. So here actually you see the 3D visualization of the data. And after doing the DSP, actually data is already in the two parts. So it's actually very easy for the model to separate them. And then once we are done with the feature extraction, we go ahead for the data training. So here actually we created the model. So you can see the edge impulse actually give you a a very nice interface to create a model. But if you are an advanced user and you just want to work with the Keras, so you go into the Keras view. So on the top, there is a menu at the top. So you can change the view as a edit mode, and you can just edit the code yourself. But I have actually chosen their view, and this is the model I have created. So for this I'm using the one-dimensional conv architecture. So there are two 1D conv with pool layer and just a flatten and using one of the dense layer. So very simple architecture. And once you are done with the model creation, you have to just click on the training button, and then it will start the training. So this is also time consuming. So I will fast forward this part. So once the training is done, so you can see there is 99.6% of the accuracy, which is really good actually. And you can see all the visualization, like what is the separation of data after the training. So it's good. And confusion matrix gives you the 100% for both of them. So this is really a good model. So why we got like very high accuracy? Because actually the DSP process already separated the data, and using the simple clustering actually separated the data. So it was very easy for the model to do this kind of thing. And then after doing the training, we can actually test the data. So while capturing the data, we already have the testing data set. So we will be using that for classifying all. Button is there. And once you click on the test data, it will try to classify on all data sets. So it will go through all the process of creating the, extracting the feature using DSP, and then generate the data and pass to the model and do the inferencing. So after the inferencing is done, you can see like all tests are passed. Everything was actually correctly recognized. And once we are done with the testing, so we can go to the deployment button here, the link actually. And in the deployment, actually, we have to choose the Arduino, since we are using the Arduino Nano BLE Sense, and just use the quantized model, which is already quantized for us using the Edge Impulse automated tool. And once we clicked on the build model, then the deployment will be created as a bundle, as a Arduino library actually, and we can download that. And we can upload that using the Arduino ID. And in the next slide, we will see the inferencing demonstration. So actually this is the recorded video, so you can just watch that.
Hello guys, I'm going to give a demonstration of Snoring Guardian. So we have an Arduino Nano BLE Sense, which is connected to this vibration motor. And we are running a TensorFlow Lite model on this. And we have a microphone on this Nano BLE Sense, which is listening for the sound. So the sound can be any noise or snoring sound. So it will distinguish between them. So I'm going to play a snoring sound, and let's see if it vibrates. So it is started vibrating. I stopped the sound, and then it will stop vibrating. So it is working correctly. Thanks for watching.
So this was the demonstration for the on-device inferencing. So I hope you enjoyed it. So yeah. So all the code and material of this session are actually available. So in the GitHub repository, so link is given here, and later Yuraj actually give you a very quick walkthrough of that repository. And actually we can also do the walkthrough of the Arduino inferencing sketch. So we can know like how we can customize this code for further, interfacing with other kind of output device maybe. So let me share my Arduino ID. So maybe I have to stop the sharing first, right? Just.
Yes.
can you see my?
Yeah, we can see your screen.
Okay, thank you. So this is the sketch actually, the Arduino sketch for the inferencing. So I will give a quick walkthrough of this the code. So first thing, actually, these are the include files. So we have to include the PDM library, which is already part of the Arduino core. And we are using scheduler. So for the scheduler, we are actually using the multi-threaded application here. And the snore detection inferencing is the part of the library, which is we generated from the Edge Impulse Studio. And we are actually using the double buffer here. So one buffer actually sample the data. And another buffer we use for the inferencing. So why we are using two buffers? Because we don't want to miss any event. So one thread actually use one of the buffer and fill it with the sound collected from the PDM microphone. And the same time, actually another thread will be doing the inferencing of the previously sampled data. So this way it will be kind of continuous audio detection application. So these are the more important thing. And actually we are doing the last 10 prediction averaging to make sure like we are doing the accurate detection. And these all are some code. Actually, you can look into the code later. So we will share everything, but I am just talking about the main point. So in this, in the Arduino Sketch, actually, the first thing is the setup function. So in setup function, I have set up the the vibration motor and the LED just for the output, and just initialize the Edge Impulse SDK here. So run classifier is the initializing actually Edge Impulse gives you the TensorFlow Lite wrapper. So everything run in the TensorFlow Lite SDK, but using the Edge Impulse API. And in the loop, so loop is actually kind of while loop. It runs, I mean, forever. And in loops, actually using the signal SDK API, we collect the sample. So microphone audio signal get data. This is the function which collects the data. And we pass this data to the run classifier continuous function, which is the part of the Edge Impulse SDK. So you just pass this thing and then it will give you all the inferencing results. And up to you, like how do you want to display the result? So in my case, actually, I am taking the average of 10 last predictions. And based on that, I just, if it is a snoring, then just vibrate the motor, otherwise do nothing. So this is the simple code, actually, you can interface in your use case. So I think I'm done with everything. So thanks for watching and listening.